Today we're going to talk about how to determine the amount of heat a recirculating chiller adds to the room. Recirculating chillers supply temperature-controlled fluid, typically water, which removes heat from a process. This heat is then transferred by the chiller to water or air. Electrical energy used by the chiller is also converted to heat, and for air-cooled chillers is added to the room. Facilities with an appropriate supply of water may also choose a water-cooled chiller, where the process heat is removed from the condenser by water. Most of the heat from the water circulation pump and the compressor is also added to this water. The remaining heat is released into the room, but is significantly less than that released by an air-cooled chiller. For the purpose of selecting either an air-cooled or a water-cooled chiller, or where to place it, it is often asked how much heat is released into the room where the chiller will be. By using the electrical data from the chiller and heat load data from the process, the amount of heat added to the room can easily be determined. To calculate energy usage, refer to the chiller's serial number tag. It should include the electrical specifications. If not, request the information from the manufacturer. The formula for converting electrical specifications to watts is shown here. Here's the power data of a powerful air-cooled chiller that can cool 10 kilowatts of heat and has a large centrifugal pump. From this data, we can calculate the maximum power consumption in watts. Thus, we know it operates on between 200 and 230 volts at 60 Hz with three-phase power. MCA, MOPD, LRA, and HP are not used for these calculations. Compressor RLA, or running load amps, indicates that the compressor uses 10.4 amps. Motor pump FLA, or full load amps, indicates that the pump motor uses 8.6 amps. Fan FLA indicates that the one fan uses 0.7 amps. This allows the amp draw to be calculated as is shown here. Because this is an air-cooled chiller, all of the electrical power used is converted to heat and ends up in the room. To complete the room heat load calculation, the application process heat is added to this calculation. For this example, add the full 10 kilowatts for a total heat load from the air-cooled chiller to the room of 17.9 kilowatts, or 60,915 BTUs. This graphic represents the worst-case load to the HVAC system from the chiller under this process load. The same chiller with a water-cooled condenser looks like this. We have 10.4 amps from the compressor, 8.6 amps from the pump motor, and 0.4 amps for the fan for a total amp draw of 19.4 amps. Then we can convert amps to watts using this formula. Adding process heat of 10 kilowatts gives a total load of 17,728 watts. While it is not much different than an air-cooled chiller, the utmost concern is where the heat ends up. First, process heat goes into the facility water supply. Next, about 94% of the compressor power is converted into heat by raising the refrigerant gas temperature during compression and is also removed by the water-cooled condenser. Pumping water also adds heat. For an approximation of pump heat into the room, we take the power usage of the pump, 3.4 kilowatts, and subtract the pump horsepower converted to kilowatts. For this example, we use a chiller with a very large centrifugal pump that is 3 horsepower. The horsepower to kilowatt conversion is shown here. So, to summarize, an air-cooled chiller will have all of the process heat from the application, plus the power used by the compressor, pump, and fan added to the room. A water-cooled chiller on the same application will have 0 process heat, 6% of the compressor heat, some of the pump heat, and all of the fan heat for a greatly reduced heat load to the room. Water-cooled chillers significantly reduce the heat that will have to be removed by the HVAC system, but they require a source of facility water that both meets the flow and pressure requirements of the chiller and can dissipate the extra heat being put into it. Conversely, an air-cooled chiller requires an HVAC system that can remove the extra heat, but is a standalone system not requiring other facility resources. Where either more chillers will be added in the future or some multiple number of chillers are going to be installed now, using water-cooled units might be a better choice, as it is typically easier to add more water lines than it is to add HVAC ducting. If just one or a few smaller chillers are added per facility, room, or area with little to no requirement for additional chillers in the future, and the HVAC system already has enough cooling capacity and airflow, then an air-cooled chiller is likely to be the logical choice.